Hello, this video is the second part of my coverage of the second chapter of HCIA Datacom version 1.0, the Network Reference Model. So in this particular video, we are going to explore Network Reference Model and standard protocols. In the first part, I discussed applications and data and how applications are the ones that generate the data that needs to be transmitted to the terminals where it will be consumed. In this video, we shall discuss the network reference model and standard protocols. But why in the first place do we need the network reference model? So networking is such a vast field that there are several protocols, several standards, and several different ways to achieve a particular objective, like any other engineering field. Because there are several different ways that can be used and several players that we call vendors in the industry, we need a way to standardize how the entire communication process happens. So we standardize this by setting up a model, and the models we are going to discuss in this part of this video or in this chapter are basically two models. We shall talk about what we call the OSI model, also called the 7-layered model, and also the TCP IP model, also known as the DoD model. We shall see how these models are all hierarchical or layered in nature, breaking down the process of communication to a way that even a beginner can understand. This makes it easier for us to interpret network communication and makes it easier for someone to get into the field. It makes it easier for us to handle troubleshooting in a rather structured way. Instead of trying to find wherever we end troubleshooting, we can troubleshoot the network layer by layer by layer. As we go along, we shall continue seeing the importance of this kind of structure. We shall also look at the different protocols, the different ways data is handled at each of the layers of these reference models. The first model I'm going to discuss with you is the OSI reference model. The OSI reference model stands for Open Systems Interconnection Model. It was included in the 7489 standard and released in 1984 by ISO or ISO, which is International Organization for Standardization in short. The OSI reference model, as I've mentioned, is also called the 7-layered model. There are 7 layers that it defines for different functions of network communication, so that we know what happens where in our network communication. We just mentioned that on the user end, an application presents information as an image, as a video, as virtual reality, as mixed reality, as augmented reality, and so on and so forth. But we also know that on the cable, this information goes as zeros and ones. How the hell does this image convert to zeros and ones? How the hell does the receiver know that these zeros and ones are indeed intended for them to receive? We need a way to modelize, we need a way to standardize this kind of conversions. The OSI model has 7 layers as illustrated in this slide. We have the application layer at the top, the one that interfaces with applications, is the one closest to the user. We have the presentation layer after the application layer, and the presentation layer is in charge of determining what the data looks like. It is the one that provides encoding and conversion of data that is sent by the application layer of one system so that it can be identified by the application layer of the receiving system. Just below the application layer, we have layer 5 in the OSI model. Layer 5 is the session layer, and its role is to establish and manage and even terminate sessions between entities at the presentation layer. Communication at the session layer is normally implemented through service requests and responses. And these service requests and responses are going to be transmitted between applications on different devices. Just below the session layer, we have what we call the transport layer. The transport layer provides transport services to the session layer. the transport layer implements either a connection-oriented connection or a non-connection oriented connection. What this means that in one way, it can first ensure there is a connection between the sender and the receiver. In another way, it doesn't need to ensure that there is a connection between the sender and receiver. It just provides the transport. We shall look at this in a little bit more detail and also look at the protocols that provide connection-oriented or non-connection-oriented communication at the transport layer. Just below the transport layer, we have what we call the network layer. The role of the network layer is to define logical addresses that in this class we shall call IP addresses. Now, please note that we have other forms of addresses like NSAP addresses, but we are not going to be discussing those ones in this class. So logical addresses, so that routing devices like routers can determine the path to send packets so that they can reach the destination networks. Just below the network layer is the data link layer. And the role of the data link layer is to encapsulate bits into octets and octets into frames. So we have bits, which are the zeros and ones that need to move on the physical layer. It encapsulates this into octets, which is basically 8 groups of zeros and ones. It encapsulates into octets, and then the octets into what we call frames. We are going to talk about frames later. After encapsulating them into frames, it uses a special way of addressing. We just talked about IP addresses here that we call media access control addressing. In order to access the media at the physical layer that is going to transmit and also provide implementation of error checking. Below the data link layer is the physical layer, and the physical layer transmits the bit flows, the zeros and ones between the devices. It defines physical specifications, electrical levels, speeds, cable pins, color codes, and things like that. These things are defined by the physical layer. So these are the 7 layers of the TCP, of the OSI model, or the 7-layered model. Now realize that I was able to very, very specifically design or specify each of the roles of each of the layers. So if your application or communication malfunctions, you know that you have to check at this layer. That is the design of the OSI reference model. One more thing I want you to note about the OSI reference model is that a layer below provides services to the layer above it, 1. 2, in the same way, it consumes the services of the layer below it. For example, the presentation layer provides a way for the application layer to present its data, provides that service. At the same time, it consumes the session service because it can't present something unless it knows there is a session for communication. The session layer provides or establishes sessions for the application and presentation layer to work. But in the same way, it needs a connection-oriented connection or a non-connection-oriented connection. It needs a connection of some kind in order to provide those sessions for the sessions to be effective. The transport layer provides transport services, connection services to the session layer. However, for it to provide the service to the layer above it, it needs to consume the addressing service. The network layer provides addressing services to the transport layer. Ladies and gentlemen, you cannot create a connection between this and this unless you know that this is A and this is B. Now, the A and B is addressing provided by the network layer. The connection is the transport provided by the transport layer. After the connection is established, the session layer can depend on the connection to set up a session. And once the session is set up, the presentation layer can use the session to determine the format of the data. Once it is determined, the application layer can feed the user with the data. I wonder whether you guys can see the hierarchy here. In the same way, we say the network layer provides logical addresses. These are logical addresses. Ladies and gentlemen, 192.168.1.7 can be held by my laptop right now. It can be held by your laptop or your phone or your tablet or your neighbor's laptop. It is a logical address. There is really no laptop in the world whose address this is. Anyone can have it. It is just logical. We need to map this address to a physical address in order to identify my laptop. That physical address is what we call the MAC address. This physical addressing is a service the data link layer provides to the network layer so that the network layer can provide more reliable addressing for the transport layer. In the same way, the data link layer provides a mode of media access so that the data that has been encapsulated from the top down can be transmitted over the link so that it is received and processed by the destination host. That is really important because understanding the OSI model helps us to understand the TCP IP model, which is the second model that we need to understand. The OSI protocol stack is complex, just as you've seen it. A lot of tasks, the service provided by this layer and this layer consuming this service, a lot of layers, a lot of, this and that new terms that are not easy to understand. And the TCP and IP protocols are the ones that are widely used today in networking. Therefore, the TCP IP reference model becomes the mainstream reference model of the internet. That is why when you're configuring IP addresses for your laptop, you see you're configuring TCP IP settings for your laptop, not OSI settings for your laptop. As such, in this slide, we try to map TCP IP to OSI model. The TCP IP model is really similar to the OSI model in structure, and it adopts a hierarchical structure, a hierarchical architecture. Adjacent TCP IP layers are closely related. That's a bit of a problem, but the standard TCP IP model combines the data link layer and the physical layer, just as you can see. It combines the standard layer, the data link layer and the physical layer. Now, as you might imagine, these layers are really performing quite different functions. And so there is going to be two kinds of functions here that are a bit far from each other. At the same time, it combines the top three layers, combines the application layer, presentation layer, and session layer into the application layer. Now, this division mode is contrary to the actual protocol formulation, because when you look at the protocols that run at the data link layer, compare them with the standards at the physical layer, these two things should not be in the same layer. In the same way, having this is quite contrary to the way OSI works. The division mode is contrary to the actual protocol formulation, as I've mentioned. Therefore, we design what we call the equivalent TCP IP model. The equivalent TCP IP model integrates the OSI model and the TCP IP standard model. The contents in the following topics in this course, in the following slides in this topic, are all talking about the equivalent TCP IP model. With the equivalent TCP IP model, we have 5 layers. We have layer 1 mapping directly to the OSI layer 1, layer 2 mapping directly to the OSI layer 2, layer 3 mapping directly to the OSI layer 3, layer 4 mapping directly to the OSI layer 4, and layer 5 mapping to the top 3 OSI layers. So ladies and gentlemen, from now henceforth, when I talk about TCP IP reference model, I'm talking about the equivalent TCP IP model. Let us start by talking about the common protocols of the TCP IP model. And as I mentioned, TCP IP here is the equivalent TCP IP. That is why we have 5 layers, layer 5, layer 4, layer 3, layer 2, and layer 1. And as you can see at the application layer, we have Telnet, FTP, TFTP, SNMP, HTTP, SMTP, DNS, and DHCP. These are just some of the protocols at the application layer. These protocols provide services for the user. For example, TFTP provides a way of transferring files. FTP also provides a way of transferring files. FTP provides a reliable but time-consuming way of transferring files. TFTP provides an unreliable but near real-time way of transferring files. SNMP provides a way of managing our network devices. DHCP provides a way of allocating IP addresses dynamically, automatically to hosts in our network. DNS provides a table for mapping IP addresses to domain names or computer names in our network. SMTP, HTTP, Telnet are just some of the networks some of the protocols at the application layer. At the transport layer, we have mainly two protocols. We have the transmission control protocol, TCP, and we have the user datagram protocol, UDP. The transmission control protocol provides reliable communication. It provides a reliable connection-oriented communication service for the application. Actually, currently, TCP is used by many popular applications. On the other hand, UDP is unreliable. Unreliable in the sense that it provides a connectionless communication that does not guarantee reliability of transmission. The reliability will be ensured by the application layer. That is so important. TCP is one of the applications that uses UDP for transport. And so DHCP, is one of the applications that uses UDP for transport. As such, because UDP is unreliable, DHCP will need to have its own reliability methods. It needs to have a way to ensure that a DHCP packet has actually been delivered. Otherwise, UDP does not care about that. That is very important. Because UDP is unreliable, when we need reliability and we are using UDP, the reliability needs to be provided by the application layer. Well, network layer is the third layer in the stack. And in network layer, we have the main protocol, IP, as regards this course. Internet protocol encapsulates transport layer data into data packets and forwards these packets from the source to the destination sites. Internet protocol provides a connectionless and unreliable service. Mark that at the back of your mind. IP is similar to UDP in a way. They are both non-connection oriented. They are connectionless. IP doesn't care whether the destination is actually there or not. If you say ping 192.168.7.7, IP does not check to see whether .7.7 is on the network. IP will simply send the packets. And if 7.7 is not on the network, there is no way IP will tell you, hey, I can't find 7.7. IP will keep silent. You will believe that 7.7 received these packets. Now, I know what some of you are thinking. Wait, John, but I have always pinged using IP and I get feedback that the ping is successful. Ladies and gentlemen, it is the unreliability of IP that leads to the design of ICMP. ICMP is a protocol that works together with IP. It sends control messages based on the IP protocol in order to provide information about various problems that may exist in the communication environment. That information will help you and me to diagnose problems and take proper measures to resolve the problems. Ladies and gentlemen, when you say ping 1.1.1.1, you're sending an ICMP echo request. That is why you're able to receive destination host unreachable, because ICMP is helping to provide error reporting services to IP. IGMP, on the other hand, manages multicast group memberships. Specifically, IGMP will set up and maintain memberships between IP hosts and their directly connected multicast routers. Now, I would like to mention that IGMP details are outside scope of this class, but those of you who will join my HCIA Datacom class, actually even within the core technology paper, we shall look at IGMP and even do labs on multicast transmission. Well, that is all about layer 3. Let us talk about layer 2 just a little bit. Now, layer 2 is the one, as I mentioned, that provides a link to layer 1. The number of protocols, Ethernet, this one is used in local area networks and metropolitan area networks. PPP is used in wide area networks. PPPoE is also used in wide area networks. We have a whole chapter dedicated to wide area networks in which we shall discuss PPP and PPPoE. For this slide right now, it's enough to know that PPP stands for point-to-point protocol and PPPoE stands for point-to-point protocol over Ethernet, a way of encapsulating PPP inside Ethernet. Now, Ethernet, we are going to talk about it quite a lot when we are talking about layer 2 protocols. Physical layer is made up of standards really that govern the communication, color coding, and other details such as those. Now, I don't know if any of you is thinking what I'm thinking, because this is Telnet, FTP, TFTP, SNMP, HTTP, SMTP, DNS, DHCP, TCP, ICMP, UDP, IGMP, IP, PPPoE, PPP, Ethernet, there is HDLC, IPX. There are just too many protocols. Where am I going? Who in the world is determining how FTP should work? Who in the world is preparing to add IPv6 or IPv10 to this? Who is doing all this stuff? Who determines PPP is PPP or PPPoE is PPP encapsulated in Ethernet? Who even gave it that name? Who is adding details, advances to these protocols? Who is cutting them short? Is there anyone who is managing these protocols? Do we have any standardization bodies? Ladies and gentlemen, we do have protocol standardization organizations. In this slide, I introduced 3 main protocol standardization organizations. First of all is the IETF, the Internet Engineering Task Force. Secondly is the IEEE, Institute of Electrical and Electronics Engineering. And thirdly is the ISO, International Organization for Standardization. Now, it is important to note that IETF is just a voluntary organization, and they are in charge of developing and promoting Internet protocols. So the protocols, those especially in the TCP/IP protocol suite, they are the ones that release new protocols or replace old protocol standards. They do that through documents that we call request for comments documents. These documents start as drafts, and after being drafts, they go ahead and are developed into other documents. Just as an illustration, I will give you the 1918 RFC on the IETF website, and you'll find we shall go to RFC 1918. Now, this is an address allocation for private internets or private networks. Private addresses are all defined in this RFC. When we read chapter 3 or chapter 4 of IP addressing, we shall talk about public addresses and private addresses. These things are defined by RFC in this RFC 1918. They are actually called 1918 addresses. For those of you who are planning on going above this level, these are the addresses we call 1918 addresses. You can see everything about them is designed here. It is a draft IETF CIDRD private address 05 updated by member 6761 network working group request for comments 1918. This is the document. And it is an update of the RFCs 1627 and the RFC 1595. It's PCP 5. And the people that were in charge of this best current practice are also enlisted right here. So the address allocation, we have the status of the memo, the motivation. The motivation is with the proliferation of TCP/IP technology worldwide, including outside and the internet itself, an increasing number of non-connected enterprises use this technology and its addressing capabilities for sole intra-enterprise communications without any intention to ever directly connect to other enterprises or the internet itself. The internet has grown beyond anyone's expectations. Sustained exponential growth continues to introduce new challenges. One challenge is a concern within the community that globally unique address space is going to be exhausted. A separate and far more pressing concern is that the amount of routing overhead will grow beyond the capabilities of ISPs. See, these are the motivations behind 1918 addresses. So these are the addresses that have been allocated: the 10/8 prefix, the 172.16/12, and the 19.168. All these, DHCP has its own RFC. DHCP has its own RFC, OSPF has its own RFC. There are different RFCs for all of these. These RFCs are documents of the Internet Engineering Task Force, and as you can see, we find them on the data tracker side of their website. So that is IETF. The second body is the IEEE. Now, in this course, we are going to talk about IEEE 802.3. We shall talk about IEEE 802.11. We shall talk about IEEE 802.1, then Q, D, W, and so on, depending on the protocol. These things you hear, IEEE, 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 have been standardized by Institute of Electrical and Electronics Engineers. It has formulated about 30% of all standards in electronics, electrical, and computer science fields worldwide. Those standards include well-known .3 for Ethernet and .11 for Wi-Fi. For those of you who are curious, you can always check out IEEE 802 standards. You will find most of the standards that define a collection of networking standards. Now, IEEE has several other standards, but 802 is for network engineering. They have other standards for security, for things like that, but these ones are for network engineering. And when you come right here, you can see quite a lot of information. My connection is a bit slow, looks to be still loading, so I cannot scroll, but you should be able to find different IEEE .what. You can see IEEE.1, this is for bridging. IEEE.2 is for a logical link. .3 is very common in this course because it defines our layer 2 main protocol. All right. Then we also have .4, which is for a token bus. We have .5, which is for a token ring. .6, which is a distributed queue dual bus system. .7 is broadband LAN practices. .8 is fiber optic practices. .9 is integrated services LAN. And .10 is interoperable LAN security. .11 is Wi-Fi. You see the popular ones. All right, we have .11a under Wi-Fi, .11b under Wi-Fi. We have .11d, which is an enhancement to A and B, but this is not a common one. .11e is an enhancement to .11, providing QoS services. .11g, we know it well. .11h, .11i. We have a number of these that we don't teach in wireless because they provide extra services. We also have .12. We have .13, .14, and so on. It is a whole host of things. So, ladies and gentlemen, there is more to this than you're actually covering here. The field is huge. all there for you to manipulate. Some of these things we find at professional level, others at expert level. I can't exhaust everything here. That's IEEE. The other body is the ISO. The ISO, in fact, is the one that developed the OSI model. So OSI is Open Systems Interconnect Model, and ISO is International Organization for Standardization. It develops the OSI model in ISO IEC 7498 publication 1. So these are some of the organizations that provide standardization to all this mess of protocols and standards that exist at the physical layer. That, ladies and gentlemen, brings us to the end of the first part, of this chapter. And the next part of this chapter is really going to be going through each of these layers slowly by slowly and talking about the major protocols at each layer. That is going to be so important because it's going to help us understand famous protocols like HTTP, like FTP, and how these protocols work. Later on, we shall have an entire chapter that dives a little bit deeper in each of these protocols. So we are going to talk about some of these protocols and the layers at which they work. And we say the fifth layer is the application layer. Now, at the application layer, we have a number of protocols. Now, one thing you should understand if you are to know how these protocols work or how these layers work is to understand that lower layers provide services to upper layers. When upper layers, because the application generates data and needs to send that data to a receiving host somewhere, the application is going to request the services of the transport layer. Excuse me, can I use your transport services? And then the transport layer will allocate port numbers to different applications. So the application HTTP needs transport layer services. You allocate them a route. The transport layer has about 65,536 routes in total, different roads. Okay, so when HTTP asked for a path, he was allocated path 80 or port 80. See, so the application layer has its paths that it calls ports, and each port has an address. So port 65,000 something, something, port 1, port 2, port 3, port 4, up to 65,535. Now, each application is mapped to a particular port number. The application hypertext transfer protocol, for example, is mapped to port number 80 of TCP. Why TCP? Because HTTP requires reliability. It's concerned about reliability. So decided to use the TCP sect of the transport layer. And in TCP, it has been allocated port 80 by default. Now, Telnet is another application layer protocol. And because it needs services of the transport layer, all these cannot be put in one huge road because they carry different kinds of data sometimes. So what happens is the Telnet has been allocated port 23 by default, TCP port 23. And then we have FTP, file transfer protocol. You want to get some file from a server to your machine or to upload some file from your machine to a server somewhere. You're using the protocol, the file transfer protocol. And that protocol uses two TCP ports. Uses port 20 for data transfer and port 21 for connection establishment. So this one used two ports. I don't know how much the transport layer is charging TCP, rather FTP, to do that. But it's using two different ports. One port for a data connection, okay? One port for data transmission, port 20, and one port for connection establishment, port 21. So one port is to make sure there is a connection. We say TCP is reliable. How does it enforce reliability? It makes sure there is a connection between the sender and the receiver, between the communicating parties. So FTP dedicates a whole port to that connection maintenance. And then SMTP uses port 25, TCP also by default. Now, TFTP, which I told you is actually FTP but the FTP that uses UDP. Okay, so TFTP requests the services of the transporter, but because TFTP is more concerned about speed or timely delivery than even reliability, what happens? He decides to leverage the technologies of UDP, User Datagram Protocol, and then operates at port 69. These are all application layer protocols. Now the number there is the port number, the layer 4 port number, the transport layer port number that port operates at. This is how FTP works. We shall only talk about the most common application layer protocols. FTP is a file transfer protocol. You have some client who wants to send a file or to receive a file from some server, which either has some files to be served out or a lot of space where you can upload your files to. So the client puts a file on the server or gets a file from the server. The FTP client provides commands for local users to operate files on the remote server. A user can install an FTP client program on a PC and set up a connection with an FTP server to operate files on the server. And then the server is the device that runs the FTP service, provides the access and operation functions for remote clients, allowing users to access the FTP server through the FTP client program and access files on the server. Another very common application, which I don't advise you to use today, is Telnet. Okay? Telnet is a standard protocol, but it is very, very old, provides remote login. So you're somewhere, and then you want to access your network devices somewhere else. Yes, they might be in a server room, and then you are in your office. They might be at your company, and then you are at home. They might be in the next room, and then you are in the previous room. They might be, the thing is, you're not on them directly. So Telnet is one of the protocols you can use for remote login. So you log into your device remotely. It provides users with an ability to operate remote devices through local PCs. Okay, that is Telnet. However, Telnet is insecure. When you're transmitting passwords over the network through Telnet, that information is sent in plain what? In plain text. If a hacker taps this connection somewhere and reads the information you're sending, then they are going to see your actual username and password in words, such as Jonathan, username, Jonathan, password, I hate jokes. They will read this exact the way it is, okay? So on the other hand, you should use SSH, which encrypts them. So even if the hacker gets them, they will find something like rubbish. They will need to run on some strong machine for about 2 weeks or even a year, depending on how your password looks like, to be able to decrypt this to text. And then HTTP, as I told you, when you open your browser and then you type in www.huawei.com, a request is sent to the Huawei server in South Africa or China. And then that server has the page you're asking for, and it sends the reply, the HTML, the hypertext markup language file that you asked for. That is how HTTP works in brief. Web page access. So there is a server somewhere that has a folder that has all the files of your website. When someone types www.jack.ug, they are directed to the IP address of this domain, of course, using DNS is the one that does that. And when they reach that domain, the server retrieves the page index.html or a particular page if it has been defined, and then returns it to the browser for display in your laptop or machine. That is HTTP. It is the most widely used network protocol on the whole internet. HTTP was originally designed to provide a method for publishing and receiving HTML pages. You should read about Tim Berners-Lee. All right, and then the transport layer, I told you, is the one that provides transportation services to the application. So the application generates the data. It needs a way to send that data to some other end. So it asks for services of the transport layer. The transport layer says, oh, cool, I have 65,000 different packs, each of them specified with an address. I can readily send you data. Wait a bit. Are you concerned with reliability or with speed? Right. Reliability says, okay, cool, I'll give you the UDP service, and then starts allocating the port numbers as required for different applications. So the transport layer protocols include TCP, which is connection-oriented and reliable protocol, defined by IETF, Internet Engineering Task Force, in request for comment document 793. So if you look for this document online, you'll find it, and all the specification of TCP will be at your ITIPS. And then UDP is a simple connectionless protocol. By connectionless, what we mean is if there is a sender here and a receiver here, once a sender has something to send, he will send. He doesn't care whether the receiver is listening, present, or absent. He has gone for a short call. He doesn't care if there is something to send. How many of you have parents who will tell you to do something even if you're not in the house? And then when you come back, they will be like, what did I ask you to do? Now, that is UDP. They will be in their bedroom and then they tell you, mop the veranda. When you have gone to buy sugar. You remember those years? And then when you're back there, what did I tell you to do? And you're supposed to answer whether you had or not. Say, I didn't hear, you had, and you're going to tell me. That is UDP. It doesn't care whether the recipient is listening or not listening. Nothing of that is his concern. What is concerned with, I have something to send, I should send. That's it. So if the receiver is listening and receives, cool. If he doesn't receive, misses a packet, no problem. Waits for the next transmission. That is UDP and is defined by IETF in request for comments document 768. So 2 protocols for the transport layer, and those protocols are all identified by ports. So TCP and UDP header, look at the TCP header and look at the UDP header. I just mentioned that TCP is very, very reliable and UDP is unreliable. Why do we say UDP is very fast? Look at its header. This is the amount of addressing information UDP adds to your data. If you have that data and you're sending it via TCP, it will say add that amount of addressing information. Information regarding which port number you're from and which application, which port number are you going to and which application. Now, if you use UDP to send that same amount of data, it will add that size of header. So which one are you going to consider? This one has a lot of details, has the source port, destination port, sequence number, acknowledgement number, header length, reserved bits, control bits, window, checksum, add, you know, each of these fields. And then the UDP header simply gives you the source port, the destination port, the length, the checksum, and the data if it's there. If it's there. Okay. Now, TCP adds a lot of overhead on our data. So it consumes a lot of our network resources. Okay. Now, each of these fields has a specific function. The source port is the one that identifies the application that sends the segment or the data. Oh, I didn't mention information at layer 4, data at layer 4 is called the segment. Okay, so at layer 4, we are not talking about data. At layer 5, we talk about the data. At layer 4, we talk about the segment. At layer 3, it has become a packet. At layer 2, it has become a frame. At layer 1, they are bit streams. Okay, You need to know those at the back of your mind. So this is a packet. Which packet is actually a segment that we got from layer 4. It is the segment received from layer 4 together with the layer 3 header, IP addressing. And then this is a frame. The frame is the packet that we received from layer 3 together with our layer 2 header and trailer. These are bit streams. That's how it goes. Now, each of these fields has an important function, and the functions are well listed in our material that you're going to find in the Telegram channel if you haven't got them already. But the source port identifies the application and the destination port identifies application. This is the application at the sender side. This is the application at the receiver side. The sequence number is the one I told you TCP is reliable. Okay? So every information, every byte that is sent is allocated a special sequence number for identification. We'll later know that I did receive byte with sequence number so and so. Okay? We use sequence numbers for identification. And then we use the acknowledgement number for acknowledgement. We use the acknowledgement number to say, okay, I received sequence number 4, now send sequence number 5. So the 5 will be the acknowledgement number. Are we getting the idea? Yes?
Yes.
Okay. And then we also have the header length, which specifies how big the header is. We have reserved and control bits, and then the window. We use the window for adjustment of the amount of data we are sending at a particular instant. The checksum is a mandatory field that we use to check the validity of the header. Someone might have tampered with this header or it is corrupt. In such a case, the checksum will fail. And then we have options and the data. So I talked about port numbers. What is happening is in your browser, you're dealing with an HTTP application. And because HTTP is concerned with reliability, it is going to work with the TCP. Now, when your application is sending, depending on your operating system, the operating system will allocate a random port number as the sending port number. In this case, we are allocating 1024 as the sending port number for HTTP and 1231 as the sending port number for Telnet. Okay. Meanwhile, for the HTTP data, it will go ahead and attach the source IP, which is over there, and the destination IP, which is the IP of the destination. Now, also the source port number, which has been dynamically assigned by the operating system, and the destination number, which is a well-known port number. Let me take you back a bit. Remember these ports? HTTP, well-known, works at port 80. Since this is an HTTP, this is HTTP data, the destination port will be port 8, but the source port will be randomly assigned. However, the number will be above 1023. Okay? From down all the way to 1023 are well-known ports. They have specific applications they work with. So the data will go, your data is the payload, or the HTTP payload, will go until it reaches TCP port 80, reaches the HTTP application, which is the web server, HTTP server, which will send a reply and a page will be displayed back in your browser. Now, when TCP is working, why do we call it TCP very reliable is because it is very careful with its connection. When it is setting up a connection, it has a mechanism called the three-way handshake. The first thing it does is to make sure there is a link between the sender and the receiver. Are we together?
Yes.
Yes, it will first make sure there is a link between the sender and the receiver. How does it know there is a link? It is going to set up a three-way handshake. Before sending data, a TCP-based application needs to establish a connection through a three-way handshake. So in our previous example, we just mentioned that TCP is sending from its port 1024 for HTTP. So in this case, the sending is at port 1024 for the IP 1111. Now, ladies and gentlemen, this thing here combine layer 3 address plus layer 4 address is called a socket. Okay, so we have the sender's socket and the receiver's socket. So what is going to happen with TCP is that the sender will first send a SYN bit. Think of it as synchronizing bit. So it sends a packet or sends a segment, a bit, with the SYN flag set. The SYN bit is set to 1. Now the sequence number is the first sequence number and acknowledgement is 0, because acknowledgement is to tell the other side that I've received your previous data, send the next one. But there is no previous data that has been sent, so this is acknowledgement 0. So sends this first bit with a SYN bit set. When PC2 receives that, he sends his own bit. Now, the sequence number is a different one for his own sequence numbers. The acknowledgement number is A+1. Now, understand this part. The acknowledgement number that this guy sends is this one's sequence number +1. What this means is, I received A, now please send the next one, A+1. That is what acknowledgement means. So he sends his own SYN bit is 1, and also the ACK bit is 1. He acknowledges what he has received and also sends his own initialization. Now this one also replies to that SYN with his ACK. Remember, this one's sequence number was B. So the acknowledgement for this sequence is to say, I have received B, now please send the next one to B. And then also his sequence number is set to the sequence number that B asked for, A+1, which was the acknowledgement. So after 1, 2, 3, a TCP connection is set up. Any question? Any question? That is how a TCP connection is set up. Once the TCP connection is set up, our communication is going to go on now. After the connection is set up, now PC1 can send the information he had to send. The sequence number and acknowledgement numbers continue from where they had reached. Okay? They proceed. And then now the payload goes with its size depending on the size of the payload. And then communication will proceed. Now, as you can see the acknowledgement number here, it is the A+1 previously received, and it's saying, I've also received the 12. The 12 is these bytes. Okay? So now you can send the what? The next one. And then you will send. Now, you can see the acknowledgement keeps on changing. Meanwhile, also this acknowledgement keeps changing. Now we have a question here. Let someone help me answer this, okay? Let me say that someone is in class. Why does the value of acknowledgement number field in segment sent by PC1 not increase? Look at this segment, okay? And see this acknowledgement is also this acknowledgement. Why is it not changing? Someone? Is someone going to answer, or should I just proceed? Okay, I should just proceed. Cool. Now we have a concept called window sliding mechanism. And what this means is, excuse me, during the TCP three-way handshake, both ends notify each other of the maximum number of bits. We call it the buffer size. So what happens, let me do this here. During the three-way handshake, these guys agree that you will be sending me 3 bytes at a time. Okay? You will be sending me 3 bytes at a time. So it says 1, 2, 3. 1, 2, 3. Okay? And then this one says, okay, cool. I have received up to 3 acknowledgement equals to 4. Now send me 4. Then, excuse me, and then after 1, 2, 3, this one says, now send me 4, acknowledgement equals to 4, and then this one sends 4, 5, 6. This one says, okay, acknowledgement is 7, and then he sends 7, 8, 9. He's sending 3, 3 because they agreed at the beginning that the window size is what? Is 3. I hope you are following. Now, what happens of 1, 2, 3, 4, 5, 6, 7, 8, 9, if in the process of sending this, 5 did not go? This acknowledgement would be, please send me 5. Even if 6 came, this one will now send 5, 6, 7. That's why we say it is reliable. Now, sometimes we agree on a window size at the beginning. We say, looks like the channel is very clear. You send 7, 7 packets. So sends 1, 2, 3, 4, 5, 6, 7. Says, okay, now send 8. 8, 9, 10, 11, 12, 13, 14. Okay, now send 15. 15, 16, 17, 18, 19, 20. Now, at some points in the communication, says send 21, 21, 22, this one fails, 24, this one fails, 26, 27. Says, hey, wait, I didn't get 24. Sends again, 24, 25 fails, 26, 27, 28 fails, 29, 30. Says, hey, wait, send 25 again. Says 25, it fails. 26 goes, 27 fails, 28 fails, 29. They say, wait. Did we say our window size is 7? Yes. I think there is a problem with the connection. Can we be sending 3 for the meantime? They adjust the window size to streamline the communication and say, okay, cool, let me send 3. It seems you're having difficulty listening to me. So they adjust now. We say send 25, but we'll only send 25, 26, 27. Say send 28, 28, 29, 30. Send 31, 31, 32, 33. and so on. When it moves so well, say, man, this communication is so sweet. I think we should increase our window size from 3 to 5. Say, okay, cool. So let me be sending 5.5. That is what window size is. It is used for adjusting the communication. So after the TCP connection is set up, the sender sends data of the specified number of bytes based on the window size declared by the receiver. After receiving the data, the receiver stores the data in a buffer and waits for the upper layer application to obtain the buffered data in its entirety. After the data is obtained by the upper layer application, the corresponding buffer space is released. Now, if the upper layer application misses out some parts of the data, those things need to be transmitted. And so the buffer space is utilized. The receiver notifies the current acceptable data size, which is the window size, according to the buffer size. That is what this slide is trying to explain. Okay? Information to do with the available buffer size and the total buffer size. This is the total buffer size. But depending on the window they have agreed on, the buffer size gets used up as the communication goes on. Once all the communication is done and has been complete, TCP will close the connection to say, no, we are done talking. I need to shut down this connection. And how it shuts down that connection is through the four-way handshake. So please note, establishing the connection is a three-way handshake. Closing the connection is a four-way handshake. For establishing the connection, we saw there is a SYN bit and the ACK bit. So the first is a SYN bit, goes. Then we receive an ACK and a SYN from the other end. And then we send an ACK. Okay, those are the 3 bits. Now for closing the connection, the first bit that is sent is the FIN bit. Okay, and then the other side sends his ACK bit and then sends his own FIN bit. This side sends his ACK. This is the connection shut down, TCP connection shut down. We say the transport layer establishes end-to-end connections, and it's the one that tears them down. So when you have a host 1 over this side and host 2 over the other side, the protocols in charge of setting up the connection between that guy and that guy before they start to communicate is layer 4. So those protocols we discussed could be TCP or UDP, depending on the requirements. If your focus is on speed, then you want to go with UDP. If your focus is on reliability, then you want to go with TCP. Now, we also say that all layers above take on services of layers below them. So layer 5, which spans all these 3, takes services of layer 4, which is transport. And layer 4 will need the services of layer 3, which is addressing, segmentation or fragmentation, and also routing. So it establishes connections between processes on hosts, and the network layer is responsible for transmitting the data from one host to another. PDUs transmitted at the network layer are called packets. I talked about this briefly last time. The PDUs or the data at layer 5 is called data or a layer 5 PDUs. Now, the layer 4 PDUs are called segments. So at layer 4, our data takes on the form of a segment. At layer 3, the PDU is called a packet, which is precisely our segment together with the layer 3 header. So the network layer is also called the internet layer, and it sends packets from source host to destination hosts. The functions include providing logical addresses for network devices, routing and forwarding data packets. So addressing routing, and then the common network layer protocols, IPv4, IPv6, ICMP, IGMP, and other protocols. So the working process of network layer protocols, particularly IP in this case, is that when they receive a packet, when they receive data, they will go on encapsulating and they will go on forwarding it based on the layer 3 addresses, which are IP addresses, based on IP addresses. So in the first place, when the sending host is sending data or encapsulating data, it will put the segment into a layer 3 header. So it will get hold of the data and add the layer 3 header, which is the source address, the destination address, and other information that we shall look at. So the letter is what the upper layer wants to send. For example, the transport layer, it is the segment. That is the letter. And then the envelope is the IP packet header or the layer 3 header, which is the sender's address, the receiver's address, all of which we are talking about IP addresses. So the PC encapsulates the IP header, which is the envelope. The key information is about source and destination IP addresses. So the network layer goes ahead and forwards routers. Routers will go ahead and forward based on the routing table that they have, that they use for forwarding packets.
Yes.
Okay. So the network layer header of a packet sent by a source device carries the network layer addresses of the source and destination devices. Each network device, such as a router that has a routing function, maintains a routing table. So the layer 3 tool is the routing table. It is the table that routers use to determine where they need to send the packets that need to be transmitted. We shall look at the details of the routing table. It is like a map of the network device. After receiving a packet, the network device reads the network layer destination address of the packet, such as the routing table for the matching entry of the destination address, and forwards the packet according to the instructions of the matching entry. So that is what happens with the network layer. We are going to have a lab to illustrate this, but I would wish to. We can actually do it. We can actually do it real fast before we proceed. So what we are talking about is, this is ENSP. I hope you can see the screen of ENSP, right?
Yes.
So this is a router here. I'm going to put a router here. And for now, I'm just going to put a PC here and a PC here. And then I'm going to connect these PCs Ethernet 001 to the routers 001. And then the router 002 to this PCs 001. Now, we said routers separate broadcast domain. So this is going to be a different broadcast domain, and this is also a different broadcast domain. On this side, I'm going to give the network 10.1.1.0/24. And on the other side, I'm going to put 10.1.2.0/24. So the PC is going to have the IP address of .10, and the router will have the IP address of .1. The same applies the other side. The router will have .1, and the PC will have .10. If any of you has any question in these short labs I'll be using to illustrate, please ask as we go on. There will not be extra time to re-explain them. I explain as I draw it up, and we shall do the configuration together. So I'm going to open the PC by double-clicking on it. and I'm going to give it the IP address of 10.1.1.10. The subnet mask /24 means 255.255.255.0, and the default gateway, the router's interface to which this PC needs to send information that is destined for a different network, is going to be the IP address here, which is 10.1.1.1. 10.1.1.1. All right, I don't need other details for now. And then PC2, I'm going to give it the IP address 10.1.2.10, subnet mask 255.255.255.0, and default gateway 10.1.2.1. All right, PCs are set. Now I'm going to set up this router just a little bit, giving it 2 IP addresses, and that's going to be all. I will go to system view first, and then let me give it a name. I'll say system name is router. And then I'll go to the interface gigabit if I need 001 and give it the IP address 10.1.1.1/24. I'll go to the interface gigabit and 002 and give it the IP address 10.1.2.1/24. All right, just to confirm, I'm going to display IP interface brief, and it will show me that I have interface gigabit bandwidth 001, which is that one, is 10.1.1.1. Yeah, that's right. And interface gigabit bandwidth 002, which is that one over there, is 10.1.2.1. That's it. Now, I don't know if any of you does realize these two are on different networks, but if you don't worry for now. I just want to illustrate, display the routing table. Excuse me, routing table. And here it is. This is the tool of the router. This is what the router uses to know what it needs to do. So right now it's saying, if anyone wants to go to the 10.1.1.0 network, I need to send that packet to my, out of my 0.0/0/1, which is that one. So the router knows if any packet comes and is going anywhere in the 10.1.1. something network, it needs to be sent that direction. And then it also knows that if anyone comes and needs to go to the 10.1.2. something network, needs to be sent to the gigabit Ethernet 00, that direction. Now, that is how, when I come to this PC and try to access 10.1.2.10, the router will know where to send the information and it should direct the information. That's it. The first 2 packets were lost because the router was looking for the entry in its routing table and it found it. Now, the last 3 packets were forwarded. If I try to ping again, all the packets will be forwarded because it now knows the entry where I need to forward the data packets.
Excuse me, John.
Yes.
The router interfaces are part of the /24 networks. Why were they showing /32 in the routing table?
Well, they were actually not showing /32. The /32 you see here, when you say /32 in the routing table, it is referring to a particular IP address, not a network. Now, /32 is a single IP address. /24 is 255 IP addresses, 256 IP addresses. Does that make sense?
Yeah. Yes, it makes sense.
So this is a network, but this is an IP address. The router knows of this network because it has this IP address on it. You realize I didn't configure, I didn't tell the router how to reach this network. Did anyone realize that?
Yes.
Yeah, but it knows because this IP address is there on the router. So it uses this IP address to determine the interface to which it should send if it is going to that network, because that IP address is in that network. So a /32, when we are writing classless interdomain routing CIDR notation, is simply to signify that this is an independent, just one IP address. It's a host IP address. And then this one is a network address. I hope that makes sense.
Yeah, thank you.
All right, you're welcome. So we're back here. This is what happens. This is what happens at the network layer. The router forwards data packets depending on where they are headed to. Well, this example I've used might not drive the point too well home, but we shall do another example that has two routers, because here the router somehow knows because it has that interface connected to that network. But there are cases where the router doesn't have the interface connected to the destination network. The destination network is far away, different from all the interfaces connected to the router. What happens in that case? And we shall see that in that case, we use some routing protocols that could either be static or any other dynamic routing protocol to determine the destination, the path to the destination network. All right, so that's the network layer. The router's job is to find the path. Actually, route is a path. The route, the word is route, but it is just a path to a particular destination, and that is what the router does for us. Now, that is layer 3. And when we come to layer 2, we have moved down one more step. Okay, we have moved down one more step. So application layer is where we have the applications that generate our data. Applications like HTTP, applications like DNS, applications like DHCP, applications like SNMP, applications like SMTP, applications like FTP, applications like TFTP, and so on. They generate our data depending on what we intend to do. The transport layer provides the application layer with transportation services by assigning each of these applications a particular path, a particular tunnel, a particular port. Each of the tunnels is labeled by a particular port number. HTTP, for example, runs at port 80. HTTPS runs at port 443. FTP runs at port 21 and 20. SSH, DNS, all those have particular ports they run at. Now, after assigning the different port numbers, the transport layer needs to know who is the host that has these port numbers that this guy needs to go to. And it needs the services of the network layer to provide addressing and also determination of the route or the path that the data needs to take. And to do that, uses layer 3 protocols like IP. That is a routed protocol. It also uses routing protocols like OSPF, and we shall talk about them. Now, once the network layer is done with the addressing and the routing, it needs services of the data link layer. The data link layer, you know, the network layer is very interesting. Determines, the network layer determines the logical address. It knows that logically, this guy is at 10.1.1.4, and logically, I'm at 10.1.2.6. So we're on different networks. The problem with the network layer is that it doesn't know who exactly is this. You know, any laptop can have this IP address, any phone can have this IP, any computer can have this IP, any server can have this IP address, any network printer can have that. So the network layer does not know who at physical layer, who exactly has this IP address. To be able to identify that guy physically, we need his media access control address. Are we following?
Yes.
Now, that is exactly the job of the data link layer. The data link layer provides the physical layer, the logical addressing of the network layer, at the same time provides the network layer the ability to access the services of the physical layer, because ultimately, your data needs to be sent through the cable. Now, it is the data link layer that understands how the cable works and understands the interface that is connected to the physical layer. It is the one where protocols like PPPPPoE will work to change your data into a frame, to change your packet into a frame, which will later on be changed into a bits and that will be transmitted over the physical medium. So the data link layer is located between the network layer and the physical layer. Excuse me. And it provides services for protocols such as IP, this is now V4, and IP, V6, at the network layer. I told you layers below provide services to layers above. Yes, your bosses, workers provide work services to their bosses, and bosses provide services to their bosses. It goes like that. So the network layer provides services to the transport layer, and the data link layer provides services to the network layer. So the protocol data units transmitted at the data link layer are called frames, which is no big deal really. A frame is simply our packet with the layer 2 trailer together with the layer 2 header. This is what a frame is. Just like a packet is what came from layer 4, which was a segment together with our layer 3 header. Just like a segment is what we received from layer 5, which is our data generated by a particular application, together with the layer 4 header. This is what it is. So a segment, our data, together with the layer 4 headers, port number, source port, destination port, and so on, becomes the segment. Now this segment goes on to layer 3. We add the layer 3 header, source IP address, destination IP address, and other things. It becomes a packet. And then our packet goes to layer 2. We add the layer 2 header, source mark, destination mark, and other details, and also the layer 2 trailer frame check sequence. We shall talk about those each briefly. And then it becomes a frame. Ethernet is the most common data link layer protocol, but we also have point-to-point protocol. We also have point-to-point protocol over Ethernet. Actually, we also have HDLC, high-level data link control protocol. So the data link layer is located within the network layer and physical layers. I've said the data link layer provides intra-segment communication for the network layer. Intra-segment means the data link layer is in between any two devices. I hope this makes sense. When we had our topology, we had PC, router, and PC. We had an IP here and an IP here. And then our layer 3 here was sending to our layer 3 layer. This is not intra-segment. Now, layer 2 only works between two directly connected devices. Does that make sense?
Yes.
It only works in that particular segment. So here we shall need that source MAC address and that destination MAC address. While the frame is still here, it is using this source MAC address and that destination MAC address. That's what we mean by intra-segment. The functions of the data link layer include framing, physical addressing, and error control. Error control is performed by the FCS. Framing is performed by addition of the FCS and the physical address, which is source mark, destination mark onto our packet. And then the common data link layer protocols include Ethernet, which is by far the most widely used, PPOE, and PPP. Okay, so Ethernet. How does Ethernet work? Ethernet and source MAC addresses. Ethernet by itself is a broadcast multiple access protocol that works at the data link layer. Broadcast means that it can carry multiple users' traffic at the same time. It's multiple access. So this guy could be sending while that one is sending. This one could be sending while that one is sending. But then that takes us into some other things we shall talk about. The network interfaces of PCs comply with the Ethernet standard. And generally, a broadcast domain corresponds to an IP network segment. We shall get to the details of this shortly. But what we are trying to say is that a broadcast domain, a broadcast domain corresponds to a single network, like 10.1.1.0/24. This will be a broadcast domain. 10.1.2.0/24. This will be another broadcast domain. Now, if you know nothing about /24 and so on, we are going to get to that. Don't worry for now. And then the addressing that Ethernet uses is called MAC addressing. It uses the media access control addresses. They are called MAC addresses, also called physical addresses. You can find the MAC address of your laptop or desktop or phone by going to its settings. For Windows, you need to go to CLI, CMD and type ipconfig/all, and it will show you the physical address. And that physical address is expressed as 6 pairs of hexadecimal digits, So a media access control address uniquely identifies a network interface card. Please note that MAC addresses identify your network interface card, not your computer. So for most of you who have laptops, you have at least 2 MAC addresses on that laptop. You have a MAC address for the Ethernet card, wired, and a MAC address for the Wi-Fi card. There are 2 different MAC addresses. It's not like, okay, and each NIC requires and has a unique MAC address. MAC addresses are used to locate specific physical devices in an IP network segment. Physical devices. A device that works at a data link layer, such as an Ethernet switch, maintains a MAC address table to guide data frame forwarding. Are we together so far?
Yes.
Now, an important aspect before I move on to the next slide, an important aspect is that we need to understand that if we have a PC connected, for instance, to a switch that is connected to another PC and maybe another PC, this PC has MAC address, for now let us say AA. This one has MAC address, for now let's say BB, excuse me. And this one has a MAC address, for now let's say CC. Also, this PC has a MAC address, let's say 1.1.1, an IP address. This is a MAC address, layer 2 address. This is an IP address, layer 3 address. This is a MAC address, layer 2 address. This is an IP address, layer 3 address, set 2.2.2.2. Also, this has a MAC address, layer 2 address, and an IP address, layer 3 address, say 3.3.3.3. Now, when this host is encapsulating data that it wants to send to PC2, it will generate the data based on the application that it is using. HTTP, for example, needs to visit a web page. Now, that data will need services of layer 4, in this case TCP, because HTTP minds reliability. TCP will need services of layer 3, in this case IP, because we are going to leverage IP addresses. And then IP will leverage routing protocols, for example, OSPF, that is still layer 3. We shall talk about that. Now, IP will need the physical, this is logical, will need the physical address. So this PC knows that I need to talk to 2.2.2.2. How does it know? Because you typed ping 2.2.2.2. So it knows I need to send a packet to the 2.2.2.2 PC. However, this PC1 needs to know who on all this network, who of this guy and this guy, who has this IP address. So this PC1 needs to map MAC addresses to IP addresses, needs to know that when I need to talk to 2.2.2.2, at physical, where the physical address is B. And when I need to talk to 3.3.3.3, the physical address is CC. This thing is what you call the app cache in your PC. You can find yours by typing app A in your CLI. So, and this is the purpose of the address resolution protocol that I want us to discuss right now, ARP. The job is to discover the MAC address that is associated with a given IP address. Please don't take that in reverse, okay? It has the IP address, but it needs the MAC address that is associated with that IP address. That's the job of ARP. Now, there are some cases, though, where we have the physical address. I know the physical address, but I need the IP address, the logical address that matches that physical address. In that case, we use what we call inverse ARP. Okay, but this case we are talking about ARP or ARP. What happens when host A with the IP address 192.168.1.1/24 needs to talk to host B with the IP address 192.168.1.2/24? You notice that host A has a different MAC address from host B. What is going to happen? Host A needs to find the MAC address of that IP address. Starts by asking who has this MAC IP address, and then host B will reply and say, I am the one with that IP address, and here is my physical. If you want to talk to me, send to that physical address. It is what happens, and then host A will then encapsulate its data. First, it checks its app cache, what I've just shown you, and finds that has nothing, so it sends an app request, the one we have seen here, sends an app request with which when host 2 receives the app request, okay, when it receives the app request, says, oh, who sent it? It's 192.168.1.1. Okay, what was the MAC address? It was that MAC address. Now host 2 puts that in his own app cache first before he even processes the data. And then he puts together, he adds it to his app entry first and then sends an app reply. An app reply is the one that will have his own MAC address. Are we together? This is the part where host 1 sends the app request. This is the information in the app request. You notice the destination MAC address is unknown, so sends it to a broadcast MAC address. Source MAC address is the MAC address of host 1. So inside the app address resolution protocol message, there is that this is a request. My MAC address is this, and my IP address is this. I need the MAC address of whoever owns this IP address. Sends that information. When that information goes to the network, of course, since it's a broadcast MAC address, the switch will send that information to any interface that is attached to it. And then, of course, host 2 will receive that information. And the first thing he does is to add the entry to his MAC address table or to his app cache, address resolution protocol cache. Says, okay, so next, if I ever want to reach host 1, I will send to that IP address who is associated with that MAC address. After entering it in his app cache, he will put together an app reply. That's the information in the app reply. Say it is a reply. My MAC address is this one. This is the MAC address that host 1 needs. Okay, my MAC address is that one, and this is my IP address. I'm sending to that MAC address and that IP address. That is the reply. And when the reply comes back, when the reply comes, after receiving the unicast frame, the switch forwards the frame, and then when it reaches this interface, host 1 enters it in his app cache. Now, when he enters it in his app cache, he's ready to send the data because he knows the physical address of the destination host. Are we together?
Yes.
All right. So that is what happens at the data link layer. At the data link layer, we have the IP address, the layer 3 address already, but we need the, remember, I told you we add a layer 2 header. Now the layer 2 header is made up of the destination MAC and the source MAC and other things. That is actually why we need ARP, address resolution protocol. Because from layer 3, we go to the destination IP address. But now we need to add the destination MAC address, and we don't know it. But since we know the destination IP address, we shall borrow the professionalism of ARP, address resolution protocol, to find the MAC address and insert it in their computer or encapsulation and send the data over our physical layer, which is going to be the cable. After that arrives at the physical layer converts the digital signal into optical signal or electric signal or electromagnetic wave, What determines which of these? 1, 2, 3. What determines which one we are converting to? We say we are converting the digital signal to either optical signal or electrical signal or electromagnetic wave, depending on what? We convert to one of these depending on whether we are using wireless transmission. If it is wireless transmission, then we shall convert to 3. If it is wired transmission, we shall convert to 1 or 2. And then in that case, if it is Ethernet, if it is coaxial cable, for example, if it is coaxial cable or twisted pairs, these ones use copper cable. We shall convert to 2, electrical. Okay. And if it is optical fiber cable, we shall convert to 1, optical. So if we are using optical fiber, we shall convert our digital signal to optical signal. If we are using a copper cable like coaxial or twisted pairs, we shall convert our digital signal to electric signal, voltage change. And if we are using wireless, we shall convert our digital signal to electromagnetic waves. Are we together?
Yes.
Right. So these are the different transmission media that I've already mentioned: twisted pairs, fiber optic cables, and then we also have serial cables and wireless.